We've seen so many different tools in the calculator over the last couple of modules, and we've talked about so many different types of distributions that I thought that I would try to organize it a little bit, because we've actually seen a lot of common themes in the last couple of modules, and those themes are also going to pop up again in Module 9. And so hopefully this starts to help organize things a little bit and gives you an idea of the type of tool that you should be using in a lot of the different problems that you're going to be solving. So this first decision tree that I have here takes us back to Module 7. And in Module 7, this is when we really looked at the three different types of normal distributions. We talked about a normal population. We talked about a distribution of sample means, the X-bar distribution. And we also talked about a distribution of sample proportions, the p-hat distribution. And in Module 7, we learned that if the distribution of sample means was going to be approximately normal, so if the central limit theorem was going to apply, the sample size needed to be at least 30, or the original population could have been approximately normal. And then the two types of tools that we used in Module 7 were inverse norm and normal CDF. And so if you were using inverse norm, where you would have been looking for a boundary or a value or a percentile, you would have said inverse norm, and remember we always put in the area to the left of some value of interest, and then we would have put in the mean and the standard deviation. But in the context of the distribution of sample means, the mean is mu and the standard deviation is sigma divided by root of n. Likewise, we looked at normal CDF a lot in Module 7. And when we were using normal CDF, we were typically finding an area or a probability. And so when we were using normal CDF with the sample mean distribution, it was often normal CDF, and then we had a lower bound or a left bound, and then we had a right bound, and then we had the mean, and once again the standard deviation. And this changed a little bit with the distribution of sample proportions. And remember, the distribution of sample proportions also had the idea of the central limit theorem, where we needed n times p to be at least 10, and n times 1 minus p also needed to be at least 10. And so those were the assumptions that we needed to make in order to say that the distribution of sample proportions was approximately normal. And again, we used normal CDF and we used inverse norm. And so with the distribution of sample proportions, normal CDF looked like this. It was normal CDF. Again, it was the left bound and the right bound. And then we had a mean, and the standard deviation was this root of p times 1 minus p divided by n. And then with inverse norm, when it was the distribution of sample proportions, it was inverse norm, and it was again the area to the left. So we say area to the left, and then it was the mean and the standard deviation, p times 1 minus p, the root of p times 1 minus p over n. So this is a recap of Module 7, and part of the reason I do this recap is because when we look at what we're going to be doing in Module 8 now, it's actually very similar. So let's take a look at our decision tree for confidence intervals. So our decision tree for confidence intervals is split up the same way, because what we've just been doing in Module 8, let's label this Module 8, is we have been trying to create these confidence intervals to estimate means, population means, and estimate true population proportions. And so we were once again working with either means or proportions, and it was once again either the distribution of sample means or the distribution of sample proportions. But our goal was a little bit different. Our goal, instead of just working with the distribution, was to estimate the true population mean, whereas down here our goal was to estimate the true population proportion. But the nice thing is the similarities really continue from the previous decision tree, because if the distribution of sample means is going to be approximately normal, then we say n needs to be at least 30, or the original population is approximately normal. And what we observed in this module was, okay, the next thing to consider is, are we given the population standard deviation or not? And if we are given that population standard deviation, and make sure you note that that stands for the population standard deviation, then the tool that we use is z-interval. But if sigma is not given, then we're relying on the sample standard deviation. So the sample standard deviation would be given, and remember, you got to really watch out for that because it can be a trap sometimes. You'll see the word standard deviation in a problem, but if you don't see that symbol sigma, then it's most likely a sample standard deviation that they're giving you, in which case we're using the t-distributions, and that's why we're selecting t-interval in the calculator. Now, when working with proportions in this module, where our ultimate goal was to estimate the true population proportion, we again needed the central limit theorem to apply. And so I think if you focus on what I've got circled here, n times p needing to be at least 10 greater than or equal to 10. I should have had an equal there also. N times 1 minus p greater than or equal to 10 also. Then the distribution of sample proportions is approximately normal, and we can continue. And the tool that we used in the calculator for this was 1prop z-int. So hopefully this helps organize your thoughts a little bit. I strongly encourage you to refer to this decision tree right now in Module 8. And when you get to Module 9, I'm going to add another one to this that's going to keep that theme of looking at means and proportions. So hopefully this helps.